Thanks a lot. It's a great pleasure for me to be, at least virtually, in Rome and Bath. So this is a joint work with Xavi Cabré and Serena Di Pierro. And actually, I gave the same title last week for a talk in Wrocław for the conference Non-Local Operators and Markov Processes. But I have a strict obligation with myself of never giving the same talk twice. So the two talks will be different somehow. So if some of you is expecting to be bored because he or she already attended this talk, the talk will be different. And specifically, I will focus in this talk more on the case of general integrodifferential kernels. But let's see what is the plan. Basically, the idea is to address the Bernstein method for integrodifferential equations. Of course, Bernstein method is a fancy way to say maximum principle. The core of the idea of Bernstein is that you can use maximum principle not for the original solution, but for some kind of auxiliary function that is constructed out of the original solution. But once you use the maximum principle to the original function, then you can derive from that some kind of bounds for the solution itself. So the method was invented by Sergei Natanovich Bernstein. Actually, I think it's a nice example of one-word mathematics already in the beginning of the 20th century, because Bernstein was a Russian mathematician from Jewish origin who wrote a paper in French published on in a German journal. So I think it's already kind of interesting from the historical point of view to notice how mathematics was already global more than 1 century ago. So the idea of the method was exactly to introduce an auxiliary function that satisfies some kind of key PDE inequality that leads to the maximum principle, and from this obtain estimates, for instance, on the gradient or the second derivative of the solution. So in the simplest possible formulation, the Bernstein method considers the solution U and an auxiliary function that is built from a cutoff. Say, for simplicity, you take eta to be C infinity compactly supported in B1, which is 1 in B1 half, and you fix a vector, say E, and you take a large constant sigma. And the auxiliary function, the simplest auxiliary function you can think of, is the cutoff square times the derivative of the solution square plus sigma times the solution itself square. And of course, this is a bit of an art to choose the right auxiliary function, but the clever idea out of this choice is that you can compute the Laplacian of this auxiliary function and use the Cauchy inequality to reabsorb a term of which you don't have control of the sign, and then choosing sigma sufficiently large, you can somehow kill the terms that have possibly the wrong sign and obtain what I will call a key inequality that says, for this specific case, that the Laplace of sigma is less than some quantity, but this quantity turns out, for instance, to be 0 when the function is harmonic. So from this, we obtain that the auxiliary function is actually subharmonic, and so we can use the maximum principle, bound its maximum, but bounding the maximum of the auxiliary function turns out by simple computations to be a bound on the interior, so in the B1 half, of the gradient of the original solution. So of course, when you deal with harmonic functions, bounding the first derivative or the second derivative is basically the same. You can take derivatives of the equation. So the Bernstein method is kind of flexible and can lead to derivative estimates in a very straightforward and elegant way. The method is also flexible enough to deal with the fully nonlinear case. This is very well expressed in the Caffarelli-Cabret's book. The typical example is the case of fully nonlinear equations driven by this nonlinear function f, which has somehow the right properties of convexity, which allow the appropriate linearization around the solution. So this is just to say that Bernstein method is general, it's flexible, it works for the fully nonlinear case, provided that the equation is convex, for instance. And again, you see from this result that in the classical case, you bound first and second derivatives with respect, for instance, of the L infinity norm of the solution itself. Now, the goal of this talk is to discuss the extension of this Bernstein method for integrodifferential equations. And of course, there are two main difficulties. One is that for the nonlocal case, one has to take into account the data at infinity. So for instance, using the maximal principle will not be enough to control the data at the boundary because there is additional information coming from infinity. And some kind of annoying fact is that the explicit computations that one can do in the classical case, based on the fact that the Laplacian is a differential operator and taking derivatives is easy, become more cumbersome, more mysterious for integral operators, and it's difficult sometimes to spot the right cancellations and the right formulation of the key inequality. This is something I will try to explain with more details later on. So the idea to address these difficulties is somehow to split the problems into two categories of operators. So the ones that admit a sort of Caffarelli-Silvestre type extension, so they can be realized by non-local operators adding one additional direction. And the general case of integrodifferential operators. And today I will try to say something more about this case as well, which is particularly interesting and I would say particularly difficult. So the two types of operators produce, at least for what we know, different types of results, because operators with extension allow results bounding not only the gradient, but also one side of the second derivative. So we can say that the second derivative is bounded from below by objects that depend on the structural constants of the equation and on the L infinity norm of the solution, basically. The setting of operators admitting an extension is also convenient because the estimates are uniform when the parameter converges to 1. So in a sense, you can really comprise all the situation from the non-local case to the local, to the classical case with one single statement. The case of integrodifferential operators with general kernels and fully nonlinear operators with general kernels are actually more difficult to analyze for several reasons. One is computational, because it's difficult to spot simplifications. And for this, we will see how we obtain a new key inequality, which is somehow less precise than the classical case, because it will include an additional error term. And this key inequality will provide a first derivative estimate. The validity of second derivative bounds for the general case remains for us an open question, and we think it's actually very interesting to understand whether it's just a technical restriction that we are not good enough to obtain the semi-concavity estimate, or there is really a structural problem that prevents the validity of these estimates. In any case, we will see that the situation is kind of tricky. The key inequality I was discussing before for the Laplacian has a natural counterpart for the fractional Laplacian. It's the one in red that I've written here. The issue is that we prove this inequality using the extension. We don't know a proof of this inequality in general without using the extension method. So basically, this forces us to deal with the general case of integrodifferential operators using a completely different strategy with respect to what we do for the fractional Laplacian. The case of operators with extension have very neat theorems, very neat results. Let me quickly present some of them. So for instance, you can consider the case of Pucci type equations, so extremal operators. For instance, you can take instead of the fractional Laplacian, an operator LA, which is like the fractional Laplacian with a rotation or with an affine transformation induced by a matrix A. And one can consider the maximal operator in which you take the sup over all the, say, elliptic matrices A in some class calligraphic A. And you can also put some kind of source term GA with reasonable continuity and compactness assumptions, and study the equation satisfied by this kind of maximal operator in this case. In this setting, you give some names to the structural constants of the equation. So G0, G1, GE1, and GE2 basically come from the structural constants of the equation. And you have kind of a neat result that says that the gradient has an interior bound controlled with the infinity norm of the solution and the structural constants. And also the second derivative has a one-side bound. One side because I'm not putting the absolute value here, I'm putting just the full second derivative. Again, it's bounded by objects that depend on the structural constants and on the L infinity norm. The statement in itself is rich because it controls two derivatives, and the proof of the theorem has to be done in just one shot. So for the classical case, you can just consider one derivative each time and differentiate the equation. But then the situation is different because remember that two derivatives are somehow too much because the equation has only two S derivatives involved. So we don't expect to have the control of the absolute value of two derivatives. So it's somehow impossible to get the result for the second derivative out of the result of the first derivative, because the result of the first derivative is a control in absolute value. Here, the second derivative cannot be controlled in absolute value. So the idea, even for this case, is to have one new auxiliary function that takes into account the first and the second derivative all together with different cutoffs that somehow compensate each other. The case of operators with extension can be pushed forward. For instance, one can consider superpositions of operators with different orders. So for instance, one I wrote here, in which you take the fractional Laplacian of order S and you average with respect to some given measure mu over all these S. Actually, I think that this type of operators are interesting, both because they are not scale invariant, so many of the techniques that are based on scaling become a little bit more tricky when you have superpositions of different operators, but also in terms of application, because if you think about the coronavirus situation, basically the countries can be divided into three groups: the countries that don't do anything about it, and the countries that do something about it by preventing the local contacts, so being very cautious in avoiding with all the means the diffusion at a very small scale, and the countries with basically avoid the long-range interaction because they close the border and they avoid the virus to navigate from one side to the other. So I think that understanding this kind of operators in which the local and non-local contributions appear and what is the effect of one or the other is somehow important also for applications. Okay, so let me try to be a little bit more quick about this, just again giving the result in which you have superpositions of different operators with respect to different measures in a fully nonlinear equation driven by nice and convex f. And again, in this situation, you can have first derivative bounds and one-sided second derivative bounds. The difference with respect to the previous case is that the operator is not scale invariant. So if the equation is set in a ball of radius r, the dependence of r in the estimates is definitely more cumbersome. But the idea is again the same. You have structural constants and you have the L infinity norm of the solution. Okay, so as I was saying, in all these situations in which the operator comes from the fractional Laplacian or from an operator which has an extension, the constants are uniform in S, are actually uniform in the number of the operators, and I'm giving the result in broad generality, but I would say that all these estimates are new, even in much simpler cases. It's just that once the method works, I think it's worth to exploit it in its full power. And also I'm presenting the results using the fractional Laplacian as building block for the operators, but you can consider powers of second order operators that are built by operators with constant coefficients, for instance, or more general objects, provided that they have an extension. Now, another thing that you can do with the method is deal with the thin obstacle problems. So another way of looking for convex nonlinear equation is to consider them, for instance, the maximum of two operators, and you can do that. This would be exactly the obstacle problem for the fractional Laplacian. And again, you can obtain first derivative bounds and one-sided second derivative bounds. Okay, very good. So what I would like now to address in further details is what happens when you don't have the fractional Laplacian, but you have a general integral operators. So I consider operators in the so-called L2 class. So operators that so kernels, operators that are built by an integral kernel, which is even, which is bounded from above and from below by the kernel of the fractional Laplacian, and which behaves well together with its first and second derivatives with respect to the kernel of the fractional Laplacian itself. So this is a class of operators introduced by Caffarelli and Silvestre with the name of L2, and somehow they are convenient because you can integrate by parts at least twice. Okay, this is important for our method, and we will see in a while the reason for being able to put some derivatives on the kernel. So the prototype operator that we consider in this setting is exactly the non-local operators in which the interaction is modeled by this kernel K. Of course, when K is 1 over Z to the n plus 2s, you have the fractional Laplacian and you have the extension. But in general, we don't expect to have extension methods available for operators which are just more or less comparable with the fractional Laplacian. So it's kind of annoying because from an analytic point of view, the operators look like the fractional Laplacian, but even a small modification of that basically prevent the use of extension methods, and so basically they prevent the use of differential computations. We really have to put the hands in the integrals in this case. Okay, so the idea in the case of general integrodifferential operators is that we want to use Bernstein method, and the core is to have a key, not differential, I would say integrodifferential inequality in this case. So we know somehow what inequality we want to expect, because in its simplest formulation, we can take the auxiliary function that is again the cutoff square times the first derivative square plus a large multiple of the solution square, and we want to apply the operator to this object. And we would like to say that this is bounded by something that has to resemble whatever we had for the case of the Laplacian and for the case of the fractional Laplacian. So I would say that it's no mystery that you would like a key inequality as the one I wrote here in the third line, but with E equal to 0. So if you think about when instead of LK, you had the Laplacian, this is exactly the first key inequality that I showed at the beginning, speaking about the classical Bernstein method. When instead of LK, you have the fractional Laplacian, is the key inequality that I said we knew how to prove it for the fractional Laplacian using extension. Now, for the general case, you would like to have a similar key inequality. So you guess that this is the result that should hold. But we are not able to prove that in this form. We need to allow an error, a small error, that can be reabsorbed somehow by interpolation in the final estimates. The issue for proving such an inequality, even with an error, is that it's very difficult to do integral computations, sure, but what is the difficulty? It's not only that differentiating is easier than integrating. This is also a difficulty, but the more severe difficulty is that it's more difficult inside an integral to spot cancellations. So whenever in the classical computation we were able to kill one term with the other because of course they were the same, here the cancellations may be hidden inside the integrals. And so we want somehow a pivot that is equivalent to the key inequality, but that has a clearer structure in terms of positivity or negativity. So one of the important observations to produce this kind of key inequalities that actually this key inequality at some point is equivalent to another inequality, which is maybe less pleasant to read because it's full of integrals, but has a structural advantage of having somehow removed the cancellations. Because if you see now, the right-hand side is made by positive terms. Now, E is an error. The error stays the same. So even with E equal to 0, these two formulations would be the same. You can also allow E to be non-zero here. And the advantage of the second formulation, in spite of the fact that it's longer, so the first formulation is 1 line, the second formulation is 3 lines, so it doesn't look like an advantage, but it's a great advantage because the terms in the right-hand side are now positive, so we exploited all the possible cancellations. So the way we use this inequality, so of course we are interested in the first inequality, but the fact is that it's easier to prove the second because one knows exactly what are the good and the bad terms. From the technical point of view, the proofs we will see deal with the second case, but of course the important inequality is the first. And the idea of dealing with the possible additional error is that the inequality that we prove is the following. So you have your auxiliary function as usual, you compute the integrodifferential operator on that. You have the right-hand side that you expect plus an error. Now the error is a small constant, say epsilon square, times the first derivative square. So the idea, roughly speaking, is that if you have this error and you want to estimate the first derivatives, you can somehow reabsorb the error into the main part by using a bit of scaling and interpolation. So this is somehow a common strategy in PDE. Sometimes you have small error caused by lower order derivatives or derivatives of the same order, but with an epsilon in front, and then you end up reabsorbing it into the main estimate. I think this was a trick used by Leon Simon, for instance, dealing also with minimal surfaces. But it's a general idea for Schauder estimates in PDEs. Okay, so about this key inequality, let me mention another open problem. Can one obtain uniform constants as S go to 1? So in this statement here, the constants depend also on S, and they are not uniform when S go to 1. just because one single integral computation depends on S in a bad way. So it's a natural question to ask whether or not it's possible to have uniform estimates. And we know that for operators with extension, you can do it. So in principle, it's possible to do it even here, but it doesn't follow from our proof. Also, another question is, can one prove the same key inequality without the additional small reminder? That is, can one set epsilon equal to 0? Again, this is true for the fractional Laplacian, but in general, we don't know how to do it. Let's discuss some specific theorems that you can use, that you can obtain using this key inequality. So again, I'm using H0 and H1 for structural constants coming from the equation. And the counterpart of the estimate for the maximal operators, so for the Pucci type equations without extension, so for general kernel, is the following. So suppose that you have a Pucci type operator. This is similar as the one we discussed before, but here it's built not from the fractional Laplacian or from a fine transformation of the fractional Laplacian, but it's built by families of general integral kernels. So you have this equation, this maximal equation, and the result is that you have a first derivative estimate, again in terms of the L infinity norm of the solution and on structural constants of the equation. Again, we are claiming here just first derivative estimates because we don't know about the one-sided second derivative estimates. So again, it would be nice to be able to state the theorem in a uniform way with respect to S, but this is an open problem, exactly because it was an open problem before for the key inequality. And as I was saying, the major open problem for us in this setting is whether or not second derivative bounds hold true for general kernels. At the moment, we only have first derivative bounds. Other examples to which our non-local Bernstein method applies is for fully nonlinear equations for convex nonlinearities. This is again very similar to what we discussed before. You have a convex fully nonlinear equation built up this time from the general integral operators instead of the fractional Laplacian. And the result is again what you expect at this point. You have a first derivative bound for the solution. And again, finding the second derivative one-side bound is an open problem. So I would like, probably I have some time at least to show some details of the proof. So as I was saying, there are two critical steps in the proof. The first is to prove the equivalence between some kind of Bernstein type key inequality with another version of the inequality in which the right-hand side has only positive terms. So this is somehow the pivotal step, because this will allow us to prove not the first inequality, but the second inequality, which is conceptually easier, and then obtain the first inequality as a byproduct. So let's see, this is somehow an algebraic computation, but let's see how you do it. So basically, you write down the first line is basically this object in the key inequality, and you want to see how far is from the second, well, you have to expand the integral operators of the auxiliary function, and you do it, and then the integral operator, it's a general fact, so I'm putting here an additional g, but I will take g as the identity later on. And once you do that, you see that there are some simplifications. You see that the terms in sigma actually simplify, because if you expand, where is it? There is a square here. So if you expand the square and you subtract this part, you cancel exactly the part with sigma in red. So the part in sigma cancels precisely. And then you end up with this, but you rearrange the terms, and you notice that this can be written in this form, and the special case of g equal to the identity is precisely the claim in the desired equivalence. But it's a general, it's a very general cancellation. A slightly harder cancellation type is needed to check the result for the solution of an equation. So I would like to give some hints of the strategy, at least for the case of S-harmonic functions. So as I was saying, for S-harmonic functions, we are able to prove the key inequality actually without the remainder. The remainder is needed if the function is not S-harmonic, if it satisfies a general integral equation. But so I would like to show this special case because it's a little bit easier, but shows already the two main techniques used in all the cases. Basically, you only have two weapons at your disposal. The first weapon is to add and subtract something. Usually you add and subtract objects which make your integral behave better. So somehow, if you have something that you are not sure it will converge or not, you will end up adding and subtracting a linear part, which makes that object quadratic, whatever it means. The second weapon in your hand is the integration by parts. So basically, all the computation I will show is a repeated use of adding and subtracting and integrating by parts, and usually both the operations done together. So again, if you want to show the key inequality for S-harmonic functions, you don't need to show the first one, you can show the equivalent one, which I wrote here. Well, I wrote here at the origin just for simplicity. In principle, you have to prove it at any point, but the origin is basically any point up to translation. So let's focus on the proof of this big inequality at the origin. And so let's call I1 the left-hand side. And the first thing is that you, integrate by parts after having added and subtracted the gradient of u equal to 0, which is 0. So if you see in this parenthesis, the gradient of u is the same of the gradient of u minus u0, because this is a constant. But this behaves better after integration by parts. And so you integrate by parts and you obtain this object. But you already put somehow a cancellation hidden in this part in which you have added 0 to the equation. Now you take advantage of the fact that the kernel is in L2, or at least the first derivatives here behaves well, and you compute the gradient of the kernel, which came from the integration by parts, and you reabsorb the gradient of the kernel into the kernel itself. So if you do this, you have I2, which I wrote here, and this unpleasant term that stays. So again, you want to integrate by parts. You want to get rid of this gradient of u of y here, but again, it's convenient to think of it as the gradient of u of y minus u of 0, so that all this part is just the gradient of u of y minus u of 0 square. And again, the square gives you an additional cancellation. Then you integrate by parts, and you have a bunch of terms. Okay, so you have a new term I3, T1, and T2, which are written here. Now, I2 and I3 are the terms that appear in the right-hand side of the equation, of the inequality, and that is the reason for which having positive terms it's better, because once you have a positive terms, you have another, well, you put them together and you don't risk additional cancellation. So whenever I see I2 or I3, even if it's 2i2, 3i3, 4i3, still fine. There are still terms that go to the right-hand side. The bad terms are still T1 and T2, which don't have a clear sign. Okay, but so for T1, one uses again the control on the kernel and integrate by parts. Well, it's a little bit of a tedious computation. Probably I don't have much time, but again, the idea is that I have to integrate by parts as much as I can. And the integration by parts will produce from T1 additional terms I2 and I3. Here I'm using the, yes, so I'm using the constant C, but the constant C is different line by line. So anytime I integrate by parts or I use the kernel bounds, I get a different constant in front, but I2, I3 are positive, so that's perfectly fine. So for T2, the situation is a little bit more tricky because one wants to better exploit the cancellation near the origin. So one has to introduce a new cutoff function zeta, which somehow localizes T2 near the origin at the price of introducing an additional T3. So I will have now to estimate not only T2, but also T3, which takes into account the part near the origin. So I have the part outside will be controlled by I3, and so I'm fine. But then I have a new T3 that has to be bound. Now, up to here, the computation is completely general. I didn't really use anything about this kernel, just that it was in the right class to estimate the first derivative. I don't think I even used the second derivative so far. I don't think I used the second derivative so far. But now I will use the second derivative here, but actually I will use something more precise. Because if you remember, I'm giving this proof only for the case in which the kernel is the one of the fractional Laplacian. When it's not the kernel of the fractional Laplacian, it's more complicated because one has to use the error term to compensate somehow the errors in the second derivative of the kernel, if you like. But for the kernel of the fractional Laplacian, there is a very nice formula that relates the Laplacian of the kernel with the gradient of the kernel. And so this provides an additional cancellation because, again, one can estimate T3 with an object which has the kernel. one can take now the gradient of the square and compute it, and add and subtract the eta times gradient u to compensate the eta times gradient u of 0. And this produces nice objects, but there is the first one, I think, which is 0, precisely for this identity here, which is specific for the case of the fractional Laplacian. So again, the general case is a little bit more involved, but relies precisely on the two tricks of adding and subtracting the right thing to have a cancellation locally, say nearby the singularity, and integrating by parts to put the derivative of the kernels whenever possible. And so this ends my talk. I think I can finish here, and I thank you for having been with me till now.